Welcome back to another explainer. Today we're doing something super exciting. We are literally taking to the skies to explore the intricate and honestly pretty mind-blowing science of aerodynamics. Our goal today is to dissect exactly how these massive, heavy aircraft somehow maintain controlled flight through what is essentially a giant invisible ocean of air.
Here is our flight plan for this explainer. First, the four forces of flight, then Newton's laws in action, understanding our atmosphere, the physics of airflow, and finally, measuring speed.
So, let's just start with the ultimate question, right? It's the one literally every single window seat passenger wonders as they look out over the clouds on a trip. How on earth does a heavy metal tube actually stay up in the sky? Think about a complex, high-performance Navy jet, and then think about a simple paper airplane you might toss across your living room. Believe it or not, they both rely on the exact same foundational principles of flight. I mean, the mechanics are completely identical. They both rely on the exact same universal laws of physics to stay aloft. It really all just comes down to a delicate, invisible balance of physical forces.
Section 1. The four forces of flight.
Okay, so there are four fundamental forces acting on an aircraft at all times. It's kind of like a giant tug of war. On one side, we have lift and thrust. Lift is that upward force generated by the wings, and thrust is the forward push coming from the engines. Together, these are the good guys. They keep the airplane flying. But on the opposing side, actively working against you are gravity and drag. Gravity is constantly pulling the mass of the airplane down toward the center of the Earth, and drag is the air resistance just stubbornly pushing back against the plane's forward movement. Those two are constantly working to shorten an airplane's flight. Now, when an aircraft flies steady and level, these four forces are actually canceling each other out perfectly. Upward lift exactly matches downward weight, and forward thrust exactly matches rearward drag. When this perfect, precarious balance happens, the airplane achieves what we call equilibrium. It isn't accelerating, it isn't decelerating, it's just cruising perfectly happily through the sky. Section 2. Newton's laws in action. You can't really talk about physics without bringing up Sir Isaac Newton, right? Aviation relies heavily on his three famous laws of motion. Let's walk through them really quick. First is the law of equilibrium, or inertia. Basically, a body at rest stays at rest, and a body in steady motion stays in steady motion unless an unbalanced force messes with it. Second is the law of acceleration. If an unbalanced force does act on the plane, say the pilot cranks up the thrust so it's suddenly stronger than the drag, the plane accelerates. That acceleration is directly proportional to the force applied and inversely proportional to the plane's mass. Heavy planes need more push. Simple enough, right? And third, we have the law of interaction, which famously tells us that for every action, there's an equal and opposite reaction. To really visualize that third law in action, just think about a spinning propeller. It creates this massive, violent rearward force, basically shoving air backward. We call that prop wash. Well, in response to pushing all that air backward, the aircraft is thrust forward with an exactly equal reaction. That invisible action-reaction pair, that is the literal physical mechanism pulling the plane through the air. Section 3. Understanding our atmosphere. So the atmosphere is, well, it's incredibly dynamic. Temperature and pressure are changing constantly based on your altitude, the weather, where you are on the globe. To actually design and measure airplanes effectively, engineers desperately needed a baseline. So they created the standard atmosphere. Check out these standard sea level metrics. Standard static pressure is 29.92 inches of mercury, standard temperature is 59 degrees Fahrenheit, and the average lapse rate, which is just how much the temperature drops as you climb higher, is 3.57 degrees for every 1,000 feet. Having these set numbers gives engineers a consistent, predictable environment to base all their math on. But here's the kicker. Planes don't always fly on a perfect standard day. And that brings us to a super vital concept called density altitude. Density altitude is officially defined as the altitude in the standard atmosphere where the air density is equal to the local actual air density. So what does that actually mean for us? Well, hotter temperatures make air expand and become less dense. So when it's absolutely sweltering outside, the air sitting right on the runway might have the exact same thin density as air thousands of feet higher up on a normal day. So the airplane effectively feels like it's taking off from a mountaintop, even if it's at sea level. So why does this matter? Well, because the air is thinner at a high-density altitude, there's literally less oxygen available for combustion in the engine, which leads to decreased engine power. Plus, there are just fewer air molecules for the propeller or the jet to actually grip onto and accelerate, which reduces thrust. This brutal combination means you get slower acceleration and, critically, you need much longer takeoff distances. This is exactly why a fully loaded passenger plane desperately needs a significantly longer runway on a hot summer afternoon. Section 4. The physics of airflow.
When an aircraft is just cruising along normally, aerodynamicists look for a condition called steady airflow. This happens when static pressure, density, temperature, and velocity remain constant over time at every single point in the flow. It's like a perfectly choreographed dance. The individual air particles follow these continuous, predictable paths called streamlines. The fluid flowing into one area perfectly displaces the fluid flowing out of the other, kind of like water rushing through a garden hose. The mass and total energy remain constant within this closed flow, which gives us that beautiful, smooth, stable movement of air over the aircraft's wings. And this nice, predictable flow, it allows us to apply Bernoulli's equation. Now don't worry, we are going to keep the math completely conceptual here. The equation simply states that total pressure equals static pressure plus dynamic pressure. Static pressure is just the ambient, everyday pressure of the atmosphere around us. Dynamic pressure is the impact pressure of the air molecules moving together. Essentially, it's the speed. In a closed system like our steady airflow, total pressure is always a constant number. It doesn't change. So think of it like a seesaw. If static pressure goes up, dynamic pressure absolutely must go down, and vice versa. The energy just constantly trades places.
Knowing this mathematical relationship between static and dynamic pressures is, well, it's fascinating physics for sure, but it leads us to a highly practical question, especially for a pilot flying a metal tube at 30,000 feet. So how do we actually measure this in the air? How does a pilot calculate their exact velocity through an ocean they can't even see? Section 5. Measuring speed. To pull this off, aircraft use what's incredibly cleverly called a pitot-static system. Here's how the whole shebang works together. A forward-facing pitot tube, which is usually stuck out on the wing or the nose, faces directly into the wind and senses the total pressure of the air ramming into it. Meanwhile, a flush-mounted static port on the side of the fuselage senses just the quiet, ambient static pressure. Inside the cockpit, a differential gauge takes these two measurements and mechanically subtracts the static pressure from the total pressure. And thanks to Bernoulli's equation, we know that whatever's left over has to be the dynamic pressure. The gauge simply translates that dynamic pressure directly into the indicated airspeed you see right there on the dashboard. It's brilliant. As we wrap up this explainer, I really want to leave you with this profound summary of energy transformation directly from our source material. Energy cannot be created or destroyed, but may be transformed. The kinetic energy of a glider in forward flight is converted into potential energy in a climb. As a glider trades forward speed to gain altitude, it's simply shifting energy from one bucket to another in this perfect physical ballet. The next time you look out the window of a flight, I really hope you have a newfound appreciation for the miraculous science happening just inches outside the glass. So, what other invisible forces are shaping the physical world around you right now, completely unnoticed? Something to chew on the next time you're hurtling through the clouds. See you next time.